is visible. So in the last class, we started combinational circuits. What I mean by combinational circuit is you will have a set of inputs and you will have a set of outputs. The number of inputs and outputs may not be the same. The number of inputs depends on the number of input variables and similarly the uh, output lines. The combinational circuit is nothing but some digital logic circuit which you will be designing. And we also saw in the last class what is the procedure to design the digital circuit, right? So from the problem statement till creating a gate level circuit is what is the procedure to design a combinational circuit. Now, so we saw some examples like half adder, full adder. When we did full adder, um, we also said something like a block level design. What I mean by block level design is there are two types, in fact, block level and gate level design. Gate level design includes all kinds of gates, whereas block level design includes a circuit which you have already designed and you just consider them as a block. So similarly, on those lines, your full adders can be implemented either using a gate level design, something like this, or since your gate level design of a full adder already consists a part of a half adder circuit, you can consider designing the full adder circuit with half adder blocks. What is the advantage here is in market, you have ready-made available ICs that will have multiple half adder blocks inside that. So it is okay if you can purchase one single half adder IC and say, for example, in this particular case, an OR gate IC, you can create a full adder circuit. If you are going for a gate level design, then you have to purchase four different kinds of ICs. One, an XOR gate IC you have to purchase. Second, you have to purchase AND gate IC and OR gate IC. Okay, so which means three different types of ICs. Now let's move on. Similarly, the design of half adders, half subtractor circuit. Again, what is a half subtractor circuit? It is a combinational circuit that subtracts two bits and produces the difference and a borrow, right? So now the calculator will be useful. Okay, so I'm going to use calculator so that you don't go wrong anywhere. Okay, so now what is that we need to do? 0 minus 0, right? Look at the binary value. It is 0, right? So this is 0. So hence it is 0, 0 here. Now next comes 0, 1. So it is 0 minus 1. You see here, it should be 0 minus 1 is okay. Yeah, this is what I wanted. 0 minus 1 is minus 1. But in the binary representation, what you see here is 1, 1, 1, 1, 1. But all we need is just 2 bits only. So we take the last 2 bits, 1 and 1. Similarly, let us subtract 1 minus 0. 1 minus 0 is 1, 0, right? So your difference is 1 and your borrow is 0. And similarly, 1 minus 1 is 0. Difference is also 0 and borrow is also 0. So likewise, you can create the truth table. Now again, what is our objective here? Our objective is to design the or to get the Boolean expression for this. So these are the ones that I'm having it here. So these corresponds to x bar y plus y bar, sorry, y bar x, right? So what is this? This is nothing but x XOR y. Okay, so which is nothing but your difference here is x XOR y. And for the borrow, you are having only one here, which corresponds to x bar y. So that is why it is x bar y is written here. Okay. Now, if you implement this circuit, then how do you implement this? You have two input variables, x and y are the input variables. So x and y are the input variables. Your difference is nothing but XOR of x and y. So XOR of x and y. And then your borrow is not of x and of y. So not of x. So this will be your x bar and this is y. So x bar y will be your borrow. Right. So we create. So this is your half subtractor circuit. Now you recall the difference between a half subtractor and a half adder circuit. The only difference here is you don't have this NOT gate in case of a half adder circuit, whereas in half subtractor circuit you have this NOT gate. Now coming to full subtractor circuit, again, what is a full subtractor is this full subtractor will take into account the uh, borrow bits also, which means that you will have three inputs here. What are the inputs? X and Y are the actual inputs, the subtrahand and the mini hand, and this particular column corresponds to the borrow that you are getting, and the last one corresponds to the borrow out, right? Say for example, I am subtracting similar to the carry out here, we have borrow out here. Again, you can create this particular truth table. The reason why I used a calculator here is this will be useful in such a scenario. Say for example, I'm subtracting, let me subtract this particular part. So what is this? This is actually x minus y minus b in. So which is 0 minus 0 minus 1. Decimally it is minus 1, but binary you will have a borrow and the difference also. So hence it is 1 and 1. Now similarly you can do any subtraction you want. Say let us do the next one, 0 minus 1 minus 0, right? This next this particular part I did. So 0 minus 1 minus 0, which is equal to, so you take the last two digits, your difference is 1 and borrow out is 1. The difference is 1 and borrow out is 1. So likewise, we can do, let us consider this particular part also, 1 minus 0 minus 1. So it is 1 minus 0 minus 1, which will be equal to 0, right? So your difference is also 0 and borrow is also 0. So your difference is also 0, borrow is also 0. So you need not apply your mind in and try to get the wrong answers. So by this way you can use simple calculators also. Now, okay, let us try 0, 1, 1 because we have got only one borrow out there. So let us try 0 minus 1 minus 1, right? What is this? Minus 2, and you see the last two decimals here, right? So your difference is 0 and borrow is 1. Okay, so your difference is 0 and borrow is 1. Hence I asked you to use this calculators. Okay. Otherwise you can do a manual subtraction also, that is also fine. Nobody stops you from doing manual uh, calculations. Okay, now coming back to the Boolean algebra simplification. Now what should we do? We must, let's remove this highlights. Okay, now we have to write the equation for this d borrow. So where are the ones you are having? You are having ones here. So this one corresponds to what? X bar, y bar, z. X bar, y bar, z. I am purposefully using z because if I'm having b in written here, it will be every time I have to carry on with this b in bar. I have to write three letters here. So hence for my sake of simplification, I have written it as z. So this corresponds to x bar, y bar, z. So we have here. And then for this particular one, this corresponds to x bar, y, z bar. So x bar, y, z bar. This one corresponds to x, y bar, z bar. So x, y bar, z bar. And last one, x, y, z, x, y, z. Now, how do you simplify? you combine. So try to combine the common terms here. So you can combine the maybe second and third you can combine, and first and the last one you can combine. So second and third, your z bar is common. So you can take x bar y plus x y bar. Similarly, you take z common from the first and the third for last minterm. So z will be common. You will have x bar y bar plus xy. What is this? This is nothing but an XNOR gate. XNOR gate is nothing but the XOR gate's complement, right? So that is what we have written here. So if you consider x bar y as say some variable a, then this equation gets simplified to z bar a plus z a bar. This can further be written as z XOR a, which is nothing but when you substitute back for a, it will be z x x XOR y XOR z. And if you want, you can replace back the z to a original form, which is nothing but your borrow in input. So similarly, so if you look at this expression, the difference expression in full adder, in full subtractor, sorry, and the sum expression in full subtractor, both the expressions are same, which corresponds to x XOR y XOR z. Sorry. Okay. Now, similarly, you can write it for the borrow expression also. So borrow corresponds to the 4 literals here. So these 3 literals and the last one. So you can further simplify it. So you take again x bar y common, x bar y common from the first and the second one. So you have z plus z bar. No, the second and the third one, and the first and the last. So take z common from the first and the last minterm. You will have xy plus x bar y. So this gets simplified to x bar y because z plus z bar is still 1, and z and the complement of x XOR y from this part. So why did we do this? Because we are already having this expression in our full subtractor expression. Where do we have this? We are having it here. So that is the reason I can use a part of my my difference output here as a part of my borrow signal. I can use this particular part. Hence, I have written it this way. Now, if you implement the same circuit using the gate level circuits, just to recall the expression here, it is the 3 inputs are X, Y, and B in. So XOR of all these 3 things. So this particular line is this is your X, Y, XOR. So you're having a XOR output here, and the other XOR output will be from your Z in. Okay, so this is your difference output. Now coming to the borrow output, what is that you have? First you have x bar y, right? So first you have to have x bar y, and this x bar y is again a part of our half subtractor, right? So half subtractor, if you recall, what is the expression? We are having x bar y as a part of the half subtractor here. So x bar y, so this particular line is nothing but your x bar y, right? So this is your x bar y. Now what is that you want? You have to OR this particular input with Z AND. So you have to first let us do this particular part. So where is the complement of X XOR Y? This is your X XOR line, and we have to take a complement of that. A complement of this has been taken. And what is this particular part? This is nothing but X XOR Y, the complement. Okay. And this has to be multiplied with what? Z. So this is your Z line. This is your Z line, right? So this line corresponds to Z dot X XOR Y, the complement. And this has to be ORed with what? This half subtractor output. So you see here, this has been ORed with this half subtractor output, okay, which is nothing but X bar Y. So this is the gate level logic. So which means that if you look at the full subtractor, again, let me erase the highlighted part so that you can visualize it better. Yeah. Okay. Now, if you look at this particular part, this is what is this? Go back and see the circuit here. This is nothing but the same circuit that you are having it here, which is your half subtractor circuit. So this is one half subtractor circuit we have, and there is another half subtractor circuit we have, this particular part, right? And you take the one. So what are the outputs here? This is going to be the difference of a half subtractor. This is going to be a borrow output of your half subtractor. Similarly, this is your difference of your half subtractor, and this particular line will be the borrow output of your half subtractor 2. So let me write it as D2, and for the first half subtractor, it is D1. So now you bring out this half subtractor's output and OR it with your. So these two outputs, the borrow outputs of the two half subtractors are ORed here. Okay, and for for the second half subtractor, what are the inputs? For the first half subtractor, these are the two inputs, X and Y are the two inputs. For the second half subtractor, what is the input here? This D1 is your one input, and the second input will be this Zn, right? So this one, this particular line, this is your second input. So if you draw a half subtractor here, I have two inputs. One is X, Y. I will have difference D1 I'll write, and I will have borrow one, borrow out actually, borrow out one. And I have one more half subtractor. One input goes here, and my Z input comes here, and my two inputs are done. So this will again have my difference and borrow. If I want my actual borrow, what should I do is I have to OR this output. So this is my actual borrow. Okay, so this is how I do a block level design. So a full subtractor will consist of a two half subtractor and an OR gate circuit, as I have done it in this block level design. So the combinational circuit, let us take more examples here. Now let us do something called as code converter. You will come across a lot of code converters in your circuit. Say for example, the best example will be your keyboards. Your keyboard has got an input of ASCII key entries. So how does your computer understands the machine languages? You have a code converter that will convert the keyboard inputs to the different machine language codes. So code converters are very, very useful devices, which is a kind of a combinational circuit. Again, why combinational circuit is you will have a set of inputs. You will have a code converter logic digital circuit here, and then you have an output code. Some examples that we can do is, if you want, you can convert a BCD to an XS3 code converter, which means that your BCD will be your inputs and XS3 will be your output. And what what are the BCD inputs, right? BCD inputs are ranges from 0 to 9, which means that 0000 till 1001, and after 10 you will have invalid entries. And what is XS3? XS3 is if you want to convert a BCD code to an XS3 code, then 0 in XS3 corresponds to 0 plus 3, which is nothing but 0011. Similarly, 9 corresponds in XS3 corresponds to 9 plus 3, which is 12, right? So what is 12 equivalent decimal value? 1010 is 10, 11, and 12. So 1100 corresponds to 12. So if you are inputting a BCD code, you will immediately get its corresponding XS3 code. So we know that XS3 code here is nothing but the decimal digit plus 3 in case of a decimals. So if n is equal to 5, then n plus 3 equal to 8. So you will have 1000 as your XS3 code. Now let us, what is the design procedure? First is the problem statement. What is the problem statement here? You have to convert your BCD code to XS3 code converter. That is the problem statement. Second, you have to identify what are the input variables and what are the output variables. Now, what are the input variables here? There are 4 input variables here and there are 4 output variables here. 4 bits, right? So this is a 4-bit, and similarly this is also a 4-bit here. So you have input variables 4 and output variables 4. Let us consider the input variables as A, B, C, D and the output variables as W, X, Y, Z. Then what you should do? You should create a truth table and you should create a relationship between them. So now let us fill it up. Okay. Now this is a decimal number. This column does not, you need not require, but just for the sake of our convenience, I have given the decimal equivalent also here. So BCD, ABCD are the inputs. So 0 decimal corresponds to 0000. And when you press 0000, your output must be 0011, which is nothing but your XS3 code. Similarly, 0001 must display 0100. Likewise, so this corresponds to 3, this corresponds to 4, this corresponds to 5, 6, 7, 8, 9, 10, 11, and 12. Now what happens after 9? After 9, we are not at all bothered. If somebody enters 10, then it is not at all nobody is going to enter 10 because your input keypads will have 4 buttons. Am I right? Each button corresponds to the BCD inputs only, A, B, C, D. Somebody may press 0000. Somebody may play around with this. Somebody will press 1100. This is not an invalid code. This is not a valid code for a BCD also. So if this is not a valid code for a BCD, you have to create a provision in your XS3 display what it should display here, right? So how are we going to design for all the invalid inputs of your BCD? That is starting from 1010, 1011, 1100 till 1111. We are going to fill don't care. We are not at all bothered if these inputs are given. It is up to your choice whether to give a don't care conditions or any other variable. If you give don't care, then what will happen is the outputs that you will get will be some random output. Say if you are giving 1111, you might get an output 1001, some random output. Next time again when you press 1111, this may change from 1100 or this may change from 0100. Some random variables you will get here. As a good design engineer, you should not have such random displays for different answers. So you can decide here what is the input we have not used here. We have not used 0000, right? So we have not used 0001. We have not used 0010. So what you can do is instead of these don't cares, what you can create is you can create 0000s and you can give it in your manual that whenever an invalid input is pressed, you will get an output of 0, right? So this is how proper design engineers must think. Okay, so we have created now a truth table and their relationship. Now what is the next procedure? For the next procedure, we have to create the K-map. We have to create K-map for this column separately, this column separately, this column and this column. So how many K-maps will be there? There will be 4 K-maps will be there. One for W, you will have a K-map. Another for X, you will have a K-map. Another for Y, you will have a K-map. And for Z, you will have another K-map, right? So we will have to simplify and get the Boolean expression for each column. And how do you fill this column? And you have 16 entries across W, right? So let us create the K-map here. I've already created. Again, W is a function of ABCD, X is a function of ABCD, y and z, they are all functions of a, b, c, d. We have to simplify using k-map. This is the k-map. So a, b, c, d. Where are the entries you have? So this is this cell is C. You can see here over a period of time with practice, I have I have avoid using the cell numbers because this comes by practice. So I can immediately say what is this particular cell number is. So 0, 1, 2, 3, 4, this corresponds to 5. This corresponds to 6, 7, right? 8 and 9. So from 5 to 9, so you see here from 5, so from 5 to 9, I'm having ones. Rest all from 0 to 4, I'm having zeros, and rest all it is don't care. So I'm having zeros elsewhere, right? And rest all don't cares. So when I can simplify this K map. So similarly, you have to do it for X column, Y column, and Z column. X column, Y column, and Z column. So what is that you get for W? W you get A plus BD plus BC. X you get B bar D plus B bar C plus B C bar D bar. So if you want, you can have this equation as it is, or you can further simplify it like you can pull out a B bar outside and still the number of gates will be the same. Okay. If you are writing this one as B bar C plus D, we have to think is how many gates are we using? How many gates are we going to use here? 1, 2, 3, 4 gates we are using. Here, how many? 1, 2, 3 gates we are using. So this one will be better. Okay. So, okay. So that is how you have to think as a designer. And when you simplify Y, you get C bar D bar plus CD, which corresponds to the XNOR gate. XNOR gate is nothing but XOR combined with a NOT gate. And for Z, it is just D bar. So if you draw this, now what is the next step? You have to represent this as a Boolean circuit or a digital circuit. So your circuit now will look like this. I am just purposefully zooming out so that I can explain you. Let's look at W. W is A plus BD plus BC. Okay. So where is A? It is A plus BD. Where is B? So this is your B line, and where is your D line? So your D line is here. Okay. So this has been simplified? Yes, this has been simplified also further. So A, sorry, A plus, this has been written this way, D plus C, right? Yes, again we can say one gate, right? So that is the reason. So now what is C plus D? So we are having, so this is an invalid thing. Yes. Now B multiplied by C plus D. So we are having C, we are having C here, and we are having D here. So this is C plus D, right? So C plus D, this is getting multiplied with B here. This is getting multiplied with B. So what is this? This is B dot C plus D, which is odd to get W, which is odd to get this W. I hope it is clear. Similarly, for X, let me erase this part. Okay. Now coming to this one, B bar C plus D, right? So here this is B, you are having B bar. This is your B bar dot C plus D. So this we already know that this is C plus D. So this particular line here corresponds to B bar multiplied by C plus D. Okay. And this has to be ORed with what? This has to be ORed with B C bar D bar. This has to be ORed with. So this is your B line. This is your C bar line. And this is your D bar line. You see here, this has been knotted and D bar has been taken out. So B C bar D bar, and you take out. So this X corresponds to B C bar D bar plus B bar C plus D. Okay, and y corresponds to C XNOR D. So this is an XNOR gate which we have used C XNOR D, and Z corresponds to D bar. So Z corresponds to D bar. So this is how you create a Boolean circuit. Now still this is not done. Now what is a combinational circuit here? Okay, yeah. Now still it is not done. What are your inputs and what are your outputs? So your inputs are, I'm just demarcating my inputs and I'm demarcating my outputs. So this is nothing but a simple block. Forget that nothing is here, right? So something black is here, right? So consider that this is a black box. Consider that this is a black box here. So all you need to do here is, right? All you need to look here is you are having four inputs. You are having four inputs A, B, C, D, and you are having four outputs W, X, Y, Z. Your ABCD inputs are your BCD inputs, and your WXY inputs are your XS3 outputs, right? So if you give four different inputs, you will get an corresponding XS3 output. So this is how you have to visualize, and you can use this particular block wherever you want to implement. So likewise, there are multiple interesting code converters. You can do it on your own. So you can also design a BCD to 84 minus 2 minus 1 code also. All you need to do is create a truth table corresponding to BCD. So you can do that. So now let's focus towards the important. We have already introduced the importance of block level design. So let us slowly move on to the importance of a block level design. As your inputs get larger and larger, what happens? Say for example, you have just designed a half adder circuit. From half adder, you designed full adder circuit or even full subtractor circuit. Now look at the complications that you had. This is your full subtractor circuit. Please note this is just for 2-bit, right? This is just for a 2-bit. X and Y are the 2 bits. What if you have a 4-bit adder or 4-bit subtractor? A 4-bit, this is a 2-bit adder. The circuit that we have designed, did we not draw this? Okay, yeah, we have, yeah. This is your half adder circuit, and this is a 2-bit adder circuit. Why 2-bit adder? Because we have got two input bits. What if we have 4 bits? What if we have 8 bits? In your computers, now you are handling 64-bit encryption. So you might require 64-bit adders. Is it possible to do this gate level design for a 64-bit adder? Please note, 64-bit adder means your inputs will be 64 bits, A, B, C, D till Z, and then A1, B1 till Z1. So how much? 26, 32 is gone. Still A2, B2 till Z2, and then A4, A3, B3 till Z4. These so many inputs are there, and creating a truth table, it is always very difficult, and gate level design will not work. So we have to move on for a block level design. How do you do this block level design? Now, as mentioned here, if you want to build a complex circuits, only block level method will be useful. Now, always these block level designs, they do not look at the input output combinations, but they always look at the algorithm. They always look at some kind of a formulae, right? So um, these algorithms or formulas, they will be helpful in decomposing your actual main problems into small problems. For example, if you want to design a 4-bit adder, you need not look at how the 4-bit addition is getting performed, all you need to think is how you can use an already available 2-bit adder and you can implement a 4-bit adder. Similarly, if you want to implement an 8-bit adder, you can look how you can use a combination of 4-bit adders and 2-bit adders, right? So that is what is the logical thinking will come when you are designing block level designs. Now, when you now let us take good examples for a block level designs. Let us take a binary parallel adder. What is this? Obviously, the one that we are performing now, they are all binary adders only. And what is a binary parallel adder? We will see once. Before, if you want to understand binary parallel adder, then you must understand what is sequential adder, right? So first we will explain what is a sequential adder. We will tell what is the disadvantage of the sequential adder, and then we will come back to this parallel adder. There are 4 different kinds of parallel adders that you can perform. Not only uh, 3 different types, but there are more kinds you can perform. You can perform the BCD to XS3 conversion using adders, the one that we just implemented using gates, right? So that you can perform using parallel adder. How you can use parallel adder? How can an adder be used in a code converter? Because if you look at the XS3 code, what is that we did? We took a decimal value n and we added 3 to it, right? This particular addition that we are performing here can be implemented in implementing an XS3 code converter, which means that we are not creating a truth table between input variables and output variables, and we are not trying to get a relationship. All we are trying to do is for the output that we are getting for an XS3, we are creating a logic of adding your inputs with 3, you will get your XS3 code. So that is what is the logic or algorithm behind this BSD to XS3 code conversions. So, and there are more applications of these parallel adders. One is again a 16-bit parallel adder. You can keep on multiplying. This 16-bit can be a 32-bit adder. This can further be expanded to 64-bit. This can further be expanded to even 128-bit adders. All these things are research topics. If you want to publish some papers, then you can implement 128-bit adders also, an efficient 128-bit adders, which reduces the adding time. And you can also perform adder cum subtractor circuit. What is an adder cum subtractor circuit? Just for the sake of understanding, let me consider a 2-bit adder. I want to design a circuit 2-bit adder cum subtractor. I want to design a circuit that performs both addition and subtraction in a single circuit. I have purposefully not taken 4-bit because that will go lengthy. For a 2-bit, so what are the inputs here? My inputs, let my inputs be X and Y. And what will be my outputs? Either I will have a sum and a carry here, or if I'm performing subtraction, this sum will be difference and this carry might be borrow, right? So now how do I create a logic? I have to have an additional input, something like a selector input. Selector input. So if my selector input is 0, right, I will perform addition. If my selector input is 1, I will perform subtraction. So I can create a logic this way. So which means that my selector input is 0, 0, my sum will be 0, 0. My selector input is still 0 and 0, 1. My sum input will be 1, carry will be 0. My selector input is 0, carry is, sorry, 1 and 0. My sum will be 1, my carry will be 0. My selector input is 0, 1 and 1. My sum will be 1, my carry will be 1. My selector input is 1 and 0, 0. My difference will be 0 and my borrow will be 0. My selector input is 1, 0, 1. So my borrow will be, sorry, 0, 0. My borrow will be 1 and my difference will be 1, right? So likewise, I can create my truth table. So you can create this truth table like this, and then you can implement both adder and subtractor in a single go. Okay. Now, as I said before, There are two kinds of adder. First, unless we don't understand the disadvantage of a parallel adder, disadvantage of a serial adder, you cannot appreciate the importance of parallel adder. So first, let us take up what is a serial adder is. Before that, your binary adders, they can be classified into two types. Not classified. You can perform addition in two ways. Either you can add serially or you can perform parallelly, right? So these one, if you are performing addition serially, bit by bit, then they are called as serial adders. If you are performing adder parallelly, then they are parallel adders. Now, what is a serial adder? Serial adder circuit will just use only one full adder circuit. Recall what is a full adder circuit is, and it will have some memory element here. Am I right? So I will have an adder, I will have a memory. Why memory? Because I want to remember that particular carry, and then I will use that particular carry as an input to my full adder. Okay, so if I'm giving uh, inputs for x and y, I can give input only one bit at a time. That is 1 and 0 I will have. This will get added and it will be stored in a memory and it will be displayed. Only the carry will be stored here. Otherwise, the sum part will be displayed outside. And this memory carry will be again fed back to your full adder here. So when my next bit comes, say for example 00 is my next input bit sequence, the 00 along with the previous carry will get added. Again, after this calculation is done, my next bit, say for example 1 and 1 is my bit sequence, that will be added with my carry that was generated in this particular stage. Likewise, you do the addition bit by bit. Okay, so what is the disadvantage here? What is the disadvantage here is this will take lot of time. This will take huge amount of time because once after the output is there, you are waiting for a carry input to be arriving. But there you have to send bits faster, right? Nowadays, bit rate is very huge, right? Even now, if we are speaking, it means that millions and millions of bits I'm sending so that it gets received by each one of you. Okay, so that is the amount of speed of bits that currently bits are traveling. If you are performing a serial addition, then there will be a huge amount of delay. Okay, so this is the disadvantage with the serial addition, which means that the simultaneous additions are not possible. So hence we go in for the parallel addition method. Now, what is the difference between a serial addition and a parallel addition is, in case of a serial addition method, how many full adders we used? We used only one full adder and a memory element. In case of a parallel adder, you will use n full adders for n bit variables. If say for example you are performing a 2-bit addition, you will use two full adders. Sorry, 2-bit addition means it is one full adder. If you are performing a 4-bit addition, then it will be a 4 full adders you will be using. So those many number of full adders you will use for those many number of bit sizes. And at the same time, your outputs will be carried from one full adder to the other as shown in this particular figure. That is, your carry here will carry forward from one stage to the next stage like this. Okay, which means that if say for example I'm performing a 2-bit addition, right? So both my inputs A, A, B and B, they are available to the full adders all the time parallelly. Only the carry gets propagated here. Okay, because it will be meaningful for this particular block to perform without this particular carry output, right? So hence this full adder, the second full adder here, must wait for the output of the carry from the first full adder. So that is the one disadvantage here. Okay, so but otherwise the calculations gets performed parallelly here. So this is the first attempt to do a parallel addition when compared to the serial addition. Obviously, this has got a disadvantage also. What is the disadvantage that this has? That is, your FA2 must wait for FA1's output. So that is the disadvantage. Okay. Now, but as soon as the carry is generated, your output will start emerging across your full adders. Okay. Now let us really jump into the design of the 4-bit parallel adder. So any doubts so far? Any doubts? Okay, all right. Now let us do the 4-bit adder. Okay, good. Okay, now let us perform a 4-bit adder. I'm slightly doubtful whether I should start this or we are into 46. Just 4 more minutes. So hence I'm doubtful. If I touch, then I have to speak a lot. I think we will start afresh maybe from the next class. Yeah, because this requires some kind of a concentration also. You must have already you have already spent a lot of time, 45 minutes of the class. So right now, if I start a thing that you have to think, then it will be slightly difficult. I think we'll stop here. Okay, so we will start this 4-bit parallel adder in the next class. Now, come afresh from the next class because it requires a lot of thinking and understanding. Yeah. Okay, so if there are no doubts, let us wind up.
Hello, sir.
Yeah.
I had some doubts in the midsem paper. I had uploaded the doubts in the discussion forum yesterday.
Yeah, then I will respond there. If still you
Okay,
are not satisfied, then again you can respond to the block.
fine, sir. Fine. Okay,
Mm,
okay, sir.
okay,
Thank you.
everything gets responded. Only emails not doesn't get responded
No, no,
because yeah, again this is not for you, for everyone. If you
yeah.
write emails, presume that this will not get responded. It is not purposefully I am doing this because I'm getting a lot of emails because everyone has got other responsibilities in the departments also, and I will be taking multiple other classes. So this is not a good way of keeping track of the doubts and issues over emails. So that is why a separate forum is there. So you can use that, and we will definitely respond. And you can also keep track of the response also. Yeah. Okay
Okay, sir.
then. Thank you so much.